Okay, so the mean value theorem. Again, one of those, basic, super important theorems in calculus that pretty much like drives calculus. This is one of those that is so well known. It's, we're on a first name basis with it. It's the MVT, okay? It's the MVT for derivatives. So, all right, so let's talk about the mean value theorem for derivatives. Again, just like with all the theorems in calculus, we read it, we think about it, and most of the time, it's something that's going to make us say, well, duh, right? So let's read this. If y equals f of x is continuous at every point on the closed interval ab, and differentiable at every point ab, then there is at least one point at which blah, blah, blah. Okay, so let's first talk about the hypothesis here. If f of x is continuous, right? We know what continuous means, right? Basically, you can draw the whole thing without taking your pencil off. No gaps, no breaks, no jumps, no vertical asymptotes. All right, so it's continuous. And differentiable at every point on its interior. What does differentiable mean? No sudden change in slope. So it's continuous. And the slope is continuous. Okay? Then there is at least one point at which something happens. Okay, what exactly is this? Look at just the right-hand side of this. F of b minus f of a over b minus a. What is that? That's average something. Yeah, that's average rate of change, right? That's average rate of change or average velocity if we're talking about speed and stuff. Good. So that's average. What's this guy? What's f prime at c? What is that? That's not average velocity. That's the slope where though? At a specific point. So if we go with what Eli said, and this is average velocity, then what is that? What kind of velocity is that? Instantaneous velocity. Good. Okay? So let's think about this for a minute. Suppose you're driving from here to whatever, and suppose, you drive 100 miles, and it takes you exactly 2 hours. What was your average speed? 50 miles an hour. Okay? Now, were you going at 50 miles an hour every single time? Like every single second that you were? No. Sometimes you were going at 80. Sometimes there was, nobody on the street, on the highway with you. You might have been going at 85. And then you see a cop. Now you're going at 50, 55, right? You might stop somewhere. Okay? So your speed was varying at any given time. But was there ever a time that when you looked at your speedometer, it read exactly 50? There could have been, right? Could there have been a time that when you looked at your speedometer, it read 50? Of course. Like if you were going 80 and you started at 0, how did you get to 80 in the first place? You had to pass through 50, right? So this is what that's saying. If you have a continuous curve, there is at least one point where the instantaneous and the average are the same. Let's think about that more abstractly in terms of a curve. So the average rate of change between A and B is this. It's the slope of the secant line, right? Right there. Average, that's the slope of the secant line. Now, let's take a look at the slope at every single point of this. The slope here, right? The tangent here, that's what it looks like. The tangent here looks like that. The tangent here looks like that. So do you see how the slope is changing little by little? The slope here is in the complete different direction. But look, when the curve is continuous and when it's differentiable, when there are no sudden changes, the slope changes so subtly that there has to be a point where the slope of the tangent line equals the slope of the secant line. Okay? So that's what we're talking about. In a more practical sense, think of the average velocity example. If you were driving at an average of 65, then there was at least one point in the drive where your speedometer read exactly 65. That's the mean value theorem for derivatives. Okay? Which kind of foreshadows that there is a mean value theorem for not derivatives as well, right? It's coming. All right. So now let's go to some of the nitty-gritty. State whether or not this function satisfies the hypotheses of the mean value theorem. So if it doesn't satisfy the mean value theorem, you can't even use it. So first you have to see whether it does. Then, if it does, find each value of c on the interval AB that satisfies the equation. All right, and it has to be on the interval given. So if you're given like 0 to 2, you can't come up with a c of 5. Okay? All right, f of x is x squared. Does this satisfy the mean value theorem? Is it continuous from 0 to 2? Is it differentiable from 0 to 2? Yeah, okay, so we can go ahead. What does the mean value theorem say? We need f prime and we need f of b minus f of a. We cannot do these in two parts, right? Divide and conquer. So first let's find f prime of x. That's just 2x. Now, if we want to get to like technical lingo, it's f prime of c, which is 2c. The only thing that does is change the variable because we're talking in c's. I haven't done math, really, just change the variable, okay? Now, what's the second half of this? F of b minus f of a over b minus a. So the first part and the second part are independent of each other so far. This is going to be f of 2 minus f of 0 over 2 minus 0. This is 4 minus 0 over 2, 2. So now what I do is connect this to this, because the left has to equal the right. 2c equals 2. c is equal to 1. Okay, that's fine. What exactly have I found? What does all this mean? What happens at c equals 1? The slopes of what are equal? Right. So at this point, right, the slope of the tangent line is equal to that of the secant line. Isn't that cool? Look, if you look at any other point, the slope is completely different. This is really cool. Come on, guys. Yeah. Okay. How about this one? Satisfies the mean value theorem? Yes or no? Well, is this function root x plus 1 continuous? Not root x, absolute value. Okay, first of all, what type of function? This is an absolute value function. Here. Who says it's continuous? Okay. Why is it not differentiable? Anytime there is a... You guys know what you're asking me. So anytime there is a sudden change in slope, there's a corner, there's a cusp, right? Vertical tangent. Okay, good. So we say MVT does not apply. Why? Because it's not differentiable at x equals 0. Now, check it out. Suppose the question was f of x is absolute value of x plus 1 on the interval 1 to 3. What then? Then it would satisfy the mean value theorem, because from 1 to 3, it's all good. Okay? So this does satisfy. So don't be, discriminatory from the get-go, right? Okay. Yeah.
If it said that derivative of that value x equals 1.
The derivative of absolute value, I haven't taught you how to do it.
Oh, so you would ask.
Right. Okay. Okay, so take a look at this one. Oh my gosh, ln of x plus 1. I don't even have my calculator. There's an e, and oh my gosh, like panicking. Okay, let's figure this out. The plus 1 says this whole thing has moved over one space. ln has a vertical asymptote at 0. Because this has moved over to minus 1, the vertical asymptote is now at minus 1. So it looks like this. Okay? We're good now. Okay, so from 0, where the heck is E? 2 point something. So from 0 to E, this satisfies the mean value theorem. So f prime of x is going to be 1 over x plus 1 times the derivative of x plus 1, which is 1. So f prime of c is 1 over c plus 1. Okay? Now, what is the formula here? The formula is f prime of c, I'm going to try to combine some steps, is f of b minus f of a over b minus a. So 1 over c plus 1 is equal to, what's f of b? ln of e plus 1 minus ln of 1 over b minus a is e. What's ln of 1?
0.
Yes. So here we have 1 over c plus 1 is equal to ln of e plus 1 over e. Okay, what do we do now?
ln is the opposite of take it out. What is it called? Ln b plus ln 1.
Oh, expand? No, we're not going to do that. We can't do that. He says cross multiply. Is there a better way? Probably. Okay, same thing. Okay, here it is. Every year, students are like mind blown by this, but here it is. When you have something like this, which is a proportion, if you flip one of the fractions, you can just flip the other one, which means c plus 1 over 1 is just e over ln of e plus 1. Is that really better? No, because I could, c plus 1 over 1 is c plus 1. What am I solving for? C. So just subtract 1. Yeah. So c is e over ln of e plus 1 minus 1. This is a rule of proportions, and we teach you back in the day. So if you have 2 over x is equal to 5 over 3, right? You just rewrite it. X over 2 is equal to 3 over 5, and then you just multiply by 2. Okay? I know. Okay. So, this is exactly what I just said. If a car accelerating from 0 takes 8 seconds to go to 352 feet, to go 352 feet. The average velocity is 44 feet per second, right? So a car starts at 0, and then it just drives 352 feet over 8 seconds. So the average is 44 feet per second, or 30 miles an hour. Was there ever a point in this time that the speedometer read 30? Well, of course. How did it get from 0 to 44 without passing 30? That's the mean value theorem. It's such a common sense sort of a thing, right? And that's what most of the theorems are. Common sense sorts of things. You just have to find that sense of it. Okay? All right. The big idea. Increasing and decreasing functions. We've all seen these before because we do them a lot in pre-calc. So if f is a defined function and x1 and x2 are some points on the interval, we say a function is increasing if for every point f of x1 is less than f of x2. Okay, what the heck does that mean? Here is x1, here is x2. This is f of x1, f of x2. If every single time f of x2 is bigger, it's higher, then this function is increasing, obviously, right? So if as you go forward, your y values are going up, it's increasing. That's how we define it. Okay, so let's take a look at this. Where does f of x increase? Over what interval? -2 to 2. Okay? I'll deal with brackets in a minute. I know you were going to ask. Okay. Decreases is the opposite. If as you're going forward, your y value is smaller every single time. So where is this function decreasing? -2 to 2. Now, you have seen this.
No, where's the -2?
Oh, sorry. From x equals -2 to x equals +2, this function is decreasing. So we read functions from left to right. And please, 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 x values only, right? It's a very common mistake where a student will say, okay, it goes from a height of 3 to -7. So let's just say 3 to -7. Don't do that because that's not right. Okay? Now, here is a little corollary. You guys remember what corollaries were? No? All that time we spent with geometry with you guys. Corollaries are just things that you can come up with from theorems. That's all. Okay, so suppose f is continuous on the closed interval AB and differentiable in the interior points. Okay, so we say if f prime is greater than 0, what does that mean? F prime is positive. The slope is positive, so it's increasing. So if the slope is positive at each point on the interior of A to B, we say that f increases on the closed interval AB. Okay? So if f is increasing, we can also say that it increases on the closed brackets. So here, we could also have said -2, 2. So, both are correct. Because if we're just looking at this, right? And if it's a closed interval, then it really starts to increase right from that point. And all the way to that point, it's increasing.
Why wouldn't one be wrong and one be right?
Why wouldn't one be right?
Yeah, why wouldn't
Because you are saying that if it's increasing just at the start, it's increasing at that point too, and vice versa.
But it doesn't include -2 though. Isn't that what you're saying?
It does. Okay. Use analytic methods to find the local extrema, the intervals on which the function is increasing and decreasing. So we're going to do what we were doing yesterday with the number line, like my favorite thing in the world, but now we're also going to add increasing and decreasing. So yay, let's do this. Okay. Huh? Oh, no. No. Domain, first we need to figure out domain is -infinity to infinity because it's a polynomial function, da-da-da-da, okay? Let's find critical points. F prime of x is 2x minus 6. F prime of x equals 0 means just that. And x is equal to 3. So, go to the number line. And I'm just going to put in x equals 3. And remember, that goes all the way to negative and positive infinity. So, we want extrema, max or min, right? Local extrema, we're doing the number line. Remember before when we were finding absolute extrema on a closed interval, what did we do? Do you guys remember? We had to plug things in. We had to test points at the intervals, at the end points and the critical points. Okay? Most common mistake students make is confuse these two. So let's be aware of that. Okay. I plug in a point on the left side, right, and it's going to give me a negative number. Here, f prime. I plug it into f prime. So 0 into 2x minus 6 gives me -6, which is negative.
Are you allowed to plug it into the original?
No, not now, no. Because I'm looking for whether the slope is positive or negative. Why am I doing that? Because if the slope is negative, the function is decreasing. So let me do another color. So far this is f prime. Now this is f and f. Okay? So, what happens at 3? We have a minimum at 3. So, the minimum, now I plug it into the original function. Where is the minimum? At x equals 3, there is a minimum. There is like a little valley. But where on the y-axis is that? Is it up here? Is it down here? I don't know. Now I plug it into the original function. So that's f of 3. F of 3 is -21. So it turns out that the minimum is all the way down here. Okay? Okay, so that's one thing I needed to find. This function is increasing from 3 to positive infinity, decreasing from negative infinity to 3. So that's what we need for this.
Those are brackets around the 3?
Yeah, or you could do parentheses, right? That's what we were talking about. Either way.
Except for the infinities. The infinities
Correct. Yeah.
Gotcha.
Okay. All right. We're going to do this one. I'm going to race you to the answer. On your mark, get set, go. Maya's slowing me down. Yes. Okay, I got what Jillian got. Right? Okay, number line. What's the domain? Negative to positive infinity. And you have 2 points. I plug numbers into where? F prime. I plug it into the factored form. Because now when I'm going to plug in a -1, here I get negative. Here I get negative. Together that's positive. Those of you who remember your multiplicities, because each of these has an odd multiplicity, the signs here will always alternate. I'll go into that a little bit later on if you don't remember. If you don't remember that, just plug in numbers. So, no, the local. So max, where do I plug in my numbers? Original. Now, it's increasing in 2 regions. Whoops. Negative infinity to 0, union 4 to infinity. It's decreasing in the middle. Either. The theorem says you could use both. If the theorem says it, it is done. Yeah, it is willed, it is done. Correct. Right, because the theorem says that f prime of c, right? Or sorry, from A to B. So these are finite points, right? Okay, this one let's do it together because it's so much fun. Okay, what is the domain? Negative infinity to -2. Correct. So basically, x can't be 2. So the domain is negative infinity 2 or -2 to -2, 2 to 2. Sorry. Okay. F prime. Now we need to find F prime. So listen, it's up to you. You want to do quotient rule or not. I minimize quotient rule as much as I can. I rewrite this as x squared minus 4 to the -1. So f prime of x, chain rule is much better, is negative x squared minus 4 to the -2 times 2x. So f prime of x is negative 2x over x minus 4 squared. I said it though. I said it. Okay? So, critical points are points where what happens? What's 0? When f prime of x is 0 or f prime of x is undefined. This has both. Okay? So, f prime of x is 0. How do we find it? It's a rational function. You set the numerator equal to 0. Okay? Now, f prime of x is undefined at x equals plus or minus 2. Huh? Yeah, so we're going to put all these in the number line. Yeah. Okay, so this is where the graph doesn't exist anyway. So, here's what we got. So if you plug in a number from like all the way to the left, it's a positive. Again, people who remember your multiplicities, at x equals -2 here, right? What's going to happen? It's going to be positive here as well. And then it's going to be negative.
Do you plug into the numerator when you're finding those again? Like to the -2x? Or
There's a maximum at 0?
Yeah.
Says maximum.
So there's a maximum at 0. And f of 0 is 1 over -4, which is -1/4. Don't do 0.25. Nobody likes decimals. -1/4. And then increasing -infinity to 0. Oh, I have one for you. Lauren, I have one for you. Suppose this function was undefined at 0. Then you would do parentheses, not brackets. Okay? Adam, everybody else too. Suppose this function was undefined at 0. Then this would be open brackets, because you can't include 0 anyway. It's not in the domain. It would be parentheses. You see that?
Oh,
It's
but
up
it
to you.
exists. Okay.
Right. Oh my gosh, what am I doing? Oh my gosh. Thank you so much. Here we go. Yeah. So, we couldn't say -infinity to 0 because that included an undefined point. So, -infinity to -2, -2 to 0, and 0 to +2. Okay?